So we've now looked at lots of properties of the cross product. We know the right-hand rule, which tells us which direction the cross product of two vectors will be oriented. We know that the cross product of two vectors will be orthogonal to the two vectors we took the cross product of. But one thing that we haven't looked at, what is the length or the magnitude of the cross product of two vectors telling us? Because given any two vectors, there's lots of vectors that could be orthogonal to them, right? So if I have two vectors here, then this vector could be orthogonal to both of them, right? But also, this much longer vector is also orthogonal. So the cross product has a particular magnitude. Is that magnitude in any way useful or relevant? Turns out that it is. So we're going to start with a lemma. A lemma is like a little mini theorem or a little mini result that you use to prove the big theorem. So this lemma is known as Lagrange's identity. So let's let u and v be vectors in R3. Then we have the following fact about the norm of the cross product of those vectors. If we take the norm of the cross product squared, then that is equal to the norm of the first vector times the norm of the second vector minus, hold up, norm of the first vector squared times the norm of the second vector squared. Minus the dot product to the two vectors squared. Okay? Now, I'm not going to prove this. The proof isn't hard, but it is a bit long and tedious. You find the cross product of u and v, you look at the formula, you take the norm, you square it, and then you simplify. And you do the same thing on the right-hand side. You plug in the component form of vector u and v, you simplify as far as you can, and you'll see that the two sides are equal. Okay, so it's not hard, but you have a lot of terms. It can get very tedious. So I'm not going to bother with a tedious and long and boring proof. Okay, but if you want to prove it, you are welcome to. But we are going to use that to prove our main result. Okay, so here's our main result. Let u and v be vectors in R3. Let theta be the included angle between u and v. Which means, by the way, that the angle would have to be between 0 and 180 degrees, right? Between 0 and pi. Because it's always the smaller angle. Then the norm of the cross product of u and v is equal to the norm of u times the norm of v times sine of the angle between them. And let me just draw a quick picture so you know what angle I'm talking about. If this is u and this is v, this is angle theta. Okay? The included angle. In particular, this is not angle theta. That's the exterior angle. That's not the one we're using. Okay? All right, so with the lemma, this proof is pretty straightforward. By the lemma, the norm of u cross v squared is equal to the norm of u squared times the norm of v squared minus the dot product of u and v squared. Okay, so all I'm doing is I'm using the lemma here, Lagrange's identity. But what do we know about the dot product? But recall that u dot v is equal to the norm of u times the norm of v times cosine of theta. Therefore, if we plug in norm of u cross v squared is equal to norm of u squared times norm of v squared minus, and now instead of u dot v, I will plug this in, norm u norm v cosine theta, and I will square it as I go. So I get norm u squared, norm of v squared, cosine of theta. Okay, and now on the right-hand side here, notice I have some factors I could pull out. From both these terms, I could pull out norm of u squared times norm of v squared. So let's go ahead and do that. Let's factor out norm of u squared times norm of v squared. If I factor that out, that leaves me with a 1 here. And if I factor out norm of u squared, norm of v squared here, all I'm left with is the cosine squared of theta. The cosine should be squared too. And now once we see this, there should be alarm bells going off in our head. This should look familiar. It's a Pythagorean identity. 1 minus cosine squared theta is equal to sine squared theta. And we are essentially done. Taking the square root of both sides of the equation, yields the result. So a couple of points here. First, we're saying we can take the square root of both sides of this equation. So I take the square root of that side, I get u cross v, norm of u cross v. Take the square root of this side, I get norm u norm v sine theta. Okay, great. You do have to generally be careful taking square roots of squares, right? Because if I take the square root of something squared, generally I get the absolute value of x, not necessarily x. So if I take the square root of sine squared theta, I would get the absolute value of sine theta. Okay. Now I don't have to worry about the norms because the square root, if I put an absolute value there, the norm's already positive. The absolute value is not going to do anything. But sine theta could sometimes be negative, right? So why in our theorem is it sine theta here and not absolute value sine theta? Well, it's because theta can only be between 0 and pi. because it's always the included angle. And between 0 and pi, sine is always positive. And so when we take the square root, we don't have to use an absolute value because sine is always positive when theta is between 0 and pi. And so the norm of the cross product, the dot product gives us information about cosine of that included angle. The norm of the cross product gives us the other piece of that trigonometric puzzle. It gives us information about the sine of the included angle. And so together, the cross product and the dot product are very powerful in telling us about the structure of vectors u and v and the relationship between them.